Okay, so as everyone starts to come in, our topic for today is factors and divisibility. So a lot of number theory, and yeah, here's a warm up. All right, so since today we're going to be covering a lot of the basics of number theory, there is a lot of content, and I think a lot of stuff that you guys might be familiar with. So feel free to just chime in whenever you want. So this warm up, I asked which numbers are prime, and this is 2, 3, 5, and 7. And we'll get into prime numbers very soon. So they're essentially just numbers that are divisible by only one and themselves. Right? So primes, what is a prime? I just said it. It's just any number p that has only factors are 1 and p. So something like 2, 3, 17, etc. And a composite number is anything that's not a prime. So 1 is a special case because it's like technically not divisible by anything except 1 itself, but like since 1 is 1, we don't really consider it prime. We don't consider it composite either. It's just 1. And the same thing with 0 is composite, but the 0 you don't really have to worry about being prime or composite because I'll get into later, primes are much more useful when it comes to factoring. All right, so their composite numbers are going to look like 4, 6, 8, 10, 9, etc. So these numbers are all divisible by a number that's not 1 or itself. So these are all divisible by 2. This is divisible by 3. So they're composite. Now you might be wondering, or you might already know, what's so important about these numbers? Why should we care whether a number is prime or not? And the main reason that we care is that primes, we can do something called factor. I don't know if there's an extra slide for this, but essentially any number can be split into distinct prime factors. So it's kind of like a way to take like this whole set of every single integer like possible and make it a bit easier to understand by having these more basic building blocks to get to these numbers. So that's kind of like what the prime numbers are. So are there any questions so far? Or all right. So Here's a fun problem to work out. Good luck. Oh yeah, also, if you want me to post just all the slides and stuff from the classes, just like I could post everything to the classroom if you guys want me to. So just let me know if you would like that. Okay, for this question, I know it's kind of tedious, so trivial is composite. Now, usually, when you're asked is some number a prime or composite, and it's some big number that does not have any obvious factors, the easiest way to solve the problem is to Google the question. But if you don't have Google, which sometimes you're not allowed to use it, what you have to do, unfortunately, is take the number and look at its square root. So 2 to 437, that's between 22 and sorry, it's between 20 and 21. And essentially, you just test every single prime number less than the square root and see if it's divisible by that number. And if it's not divisible by any number less than its square root, then that means that it is prime. And the reason why this is the case is because if, for example, it's divisible by a number greater than its square root, then it must also be divisible by a number less than its square root, or else like those two numbers multiplied together won't be equal to said number. So it's just a neat trick. So essentially you just test 2, 3, 5, 7, 11, 13, and 17, and 19. And of course, the last one works like that. So yeah. All right. Okay, next one. I'm not going to make you do this, but it's this. So it's kind of still the same thing. You just test the small ones up till the square root, which is somewhere like 30 something. And yeah, so once you see it's divisible by 7, like you do some long division, and it looks like something times 143. And then 143 is divisible by 11 and 13, as shown here. So that's like the process of prime factorization, where we take the big number and split it into a product of some prime numbers. And the important part is that each number has a unique prime factorization. So essentially, each one, like if we know its prime factors, like how many of each prime number multiplies to get to it, then we can know what this original number is, and vice versa. So this might seem pretty intuitive, and that's because it is. But just know that the fact that this is a unique prime factorization is pretty important. Right. And here's another one, and this one is not. This one is prime. So if you want to check it on your own, you can, but there's really no great way to verify this unless you go through every single factor. Okay, so I've been talking a lot about primes and factorizations and stuff, so this is probably the best time to explain it. So how do you factorize numbers? So let's just say we have 42. So how do we factor this? How can we split 42 into a product of prime numbers? So let's go ahead and work on your own for like a minute or so and discuss. Right, so it's 2 times 3 times 7. Now, how did we get here? I mean, I think many of you will know that this is just 6 times 7 is 42. And from there, you can split 6 into 2 times 3. So 2 times 3 times 7. Right? But what if we have a larger number that you might not know off the top of your head, like 192? Oh, this is a very 192. How would we go about factorizing this? Right, we make observations about the number. So, which we'll get into a little bit later, which is in the divisibility portion. But essentially, the easiest thing to do is see that it's an even number. So we can just divide by 2. And this is equal to 96. Okay, and then do this process again. 96 is also divisible by 2. So this is 48. And then we can just keep on doing this. I mean, this kind of works out since it's you'll see. But we just keep on like finding just any single prime and just keep dividing it out until you get another prime number. So this one is a little bit long since it's all like 2. So and in our end, we can kind of work backwards. So it's just 3 times 2 is 6. Alternatively, if you notice that this was divided by 3, you could have done 192 divided by 3, which is 64. And 64 is just 2 to the 6. But either way, this is just meant to be an example of the process by which you factor. So as I'll get into later, from just looking at the number, you can always, or not almost always discern prime factor of it. And then from there, you can, go do this process. So the next part is how do you count factors? And this is not important. I think it should mean how do you count divisors. So first we should define what divisor is. A divisor of a number is simply any number that divides that number. So for example, 3 is a divisor of 192. So is 2. So is 96. So is 48. And etc. Right? So the question is, how many numbers divide 192 evenly? And by evenly, I mean no remainder. So why don't we, I'll just step through this. So first, as the naive approach would simply be to list everything out. And I think that this is probably the, okay, well, actually, since people are getting it, maybe I won't do that. Right, it's 14. And this is a very important trick to know, where essentially, with here, it's just 2 times 7 because you add 1 to each of these exponents and then multiply them together. More rigorously, if we have any kind of factorization, so let's just say it's P1 to the n and P2 to the n and P3 and the k. And let's just say that for whatever, sorry, without loss of generality, let's just say that there are 3 prime factors, and we can this generalizes to any number of prime factors. And these are all the exponents that we have for each prime factor. It doesn't matter what value they are. If a prime number doesn't exist in the factorization, then this exponent is just 0. And you simply just take each 1 plus 1 and multiply them together. And this is the number of divisors. And the reason why this works is because you can think of this as you're creating a divisor by just choosing the number of like these prime factors you want to put into the number. So essentially, if n plus 1 represents the numbers from 0 to n, this represents the numbers from 0 to m, and this represents the numbers from 0 to k. So as a whole, this product describes a way to choose 3 values from each of these groups so that they're assigned to the exponent of each of the prime factors. And then when you multiply that out, you're guaranteed to get a divisor because each of the exponents is less than or equal to the one in their original number. So if you want to explore, and this is actually a pretty cool concept. This is an example of, although kind of a little bit of a strange one. It's an example of a generating function. And so if you're curious, this is more than algebra. It's like an algebra and counting kind of idea. If you're interested, you should look into this. And I will say that it is very cool. So yeah, check it out. Anyway, are there any questions on this? All right, I guess we move on to Lcms and Gcds. And so what do these abbreviations stand for? Does anyone know? Right, the lowest common multiple or least common multiple? Yep, GCD is greatest common divisor. So you can treat these as a function, sort of, with taking some number of inputs. Usually it's 2 because that's the most simple. Where the LCM of the LCM of 2 numbers, m and n, is just the smallest number, let's say k, such that m and n both divide k. So for example, if we have 2 and 3, then the LCM of that is 6. If we have something like 4 and 6, the LCM is 12. And so on. Notice that this LCM must be greater than or equal to both of these numbers. Otherwise, by definition, it would not be a multiple. And a GCD would be the greatest number that divides both of these. So if we have our examples again of 2 and 3, then the GCD is just 1, because these numbers are something called relatively prime, meaning that they have no common divisors other than 1. And if you have 4 and 6, then the GCD would be 2, because 2 is the greatest number that divides both 4 and 6, right? And so there are, I think, 2 big things to know about these functions. First one is that the way to calculate that is just factorize both of the terms m and n, and then once you have the prime factorizations, for LCM, you take like the greatest power of each prime number that appears in each factorization. So for 4 and 6, we have this is 2 squared. It's a 2 times 3. So we take the 2 squared from the 4, and we take the 3 to the 1 to the 6 to get 12. GCD works opposite. So 4 is 2 squared, and 6 is 2 times 3. So now we take the lowest exponent from each prime number, right? So that means we take this 2 here, because this is 2 to the 1, it's less than 2 squared. And we take the 3 to the 0 in the 4's factorization. So since there's no 3 there, we just take the 0. And so this leaves with 2. And so this would be kind of a basic example of how you would calculate them. Right, and then the last important thing to know is that the LCM, this is of 2 numbers, LCM of 2 numbers times the GCD of these 2 numbers is always equal to the product of the 2 numbers themselves. So you notice that 4 times 6 equals 24, 12 times 2 also equals 24. 2 times 3 equals 6, 6 times 1 is also equal to 6. And I think that if you look a little bit closely into the method to calculating each of them, I think this provides a lot of insight into why this is always true. It's simply because if we look at each like prime term, I guess you'd say, it's always going to be in exactly one of the LCM or GCD, because it's either greater than or less than. If it's equal to, then it doesn't really matter which one you choose. So it's either greater than or less than its corresponding term in, that's not the right arrow, it's the corresponding term in the other number. So if we look at the 4 and 6, the 2 squared and the 2, they're corresponding. And then LCM, you choose the 2 squared. And GCD, you choose the 2. And with this 3 to the 0 and 3 to the 1, in the LCM, you take the 3 to the 1, and GCD, you take the 3 to the 0. And what ends up happening is that every single one of these prime terms in both of the numbers is chosen exactly once. So when you multiply them all together, it must be the same product on both sides, because all the prime factors are going to have like the same exponents. And since every number has a unique prime factorization, these 2 numbers must be the same. All right, does that make sense? All right, well, okay. So last thing, we create an algorithm. And I'll get into more examples here. And I think it's a lot easier to understand with a problem. But just know for now that it's just a way to calculate GCDs of bigger numbers that might be difficult to factor. So this is just easier way to calculate GCD. And from this formula, it's also easier way to calculate LCM. So easier GCD. And I'll put this off until a little bit later. Okay. So are there any questions on this entire slide? Alrighty. So I guess now there are a lot of problems, so we'll just work through them. All right, so for everyone who's responded is correct. Okay. The answer is 3 squared times 5 squared. And essentially, since 225 is obviously a multiple of 5, that's probably where most people should start out with. And when you divide it out, it's just this. This is a 45, we divide by 5. And then 45 is just 9 times 5, and then that's where you get from there to there. Yeah. Or you could notice that this is just 15 squared, which also makes it pretty easy. Right. Excellent. All right, I just realized that this problem isn't worded correctly. I probably meant to say divisors here. So yeah, that probably would change the answer. Yeah, okay. We can do both. So anyway, for the divisors question, there are 24 divisors, and there are actually 5 or 4 factors, depending how you look at it. So 420 is just 2 squared times 3 times 5 times 7. So there are 4 different prime factors you can see, 2, 3, 5, and 7. And there are 3 times 2 times 2 times 2, or 24 divisors. I should have been more specific with my wording. So yeah, that's for both of them. All right. Move on. And this, again, just treat the word factors as divisors. Yep, whoever's answered so far is correct. Yeah. So the correct answer here is 16. So 1000 is just 2 cubed times 5 cubed. This is pretty easy to see since it's equal to 10 times 10 times 10, and 10 is 2 times 5. So we just take it 3 times. So that's why it is a cube. And then since I'm using divisors here, this is just 4 times 4 equals 16. Just add 1 to both of them, multiply them together. Right. I think we have a couple more of these. So again, treat this as divisors. All right. Okay, so we only have a minute left in this meeting. I'll just go over this one real quick. This is 4. And things do change when you when talking about divisors. 22 is 2 times 3 times 7. And so since we only want the odd ones, this means that we can ignore the 2. And so how many divisors of 3 and 7 are there? It's just, 2 times 2 or 4. And these ones are 1, 3, 7, and 21, which you can kind of list on your hand. All right, so that does it for this session. I'll see you in about a minute for the next meeting. All right, so just be sure to
bye.
All right, so as we're waiting for everyone else to rejoin, why don't we try this out? Okay, so I see a few people have the right answer. It's 63. So I'll first go over the way that I think we know right now, which is prime factorization. So as we'll get into a little bit later, both these numbers you can see are divisible by 9. And if you can't see, you should be able to see after next slide, which is kind of out of order, but Okay, these are both divisible by 9. So 819 is 9 times 91. And 91 is actually 7 times 13. So this is 3 squared, 49 times 7 times 13. And 504 is divisible by 9. It's also divisible by 4. So you can kind of choose which way to go, but essentially this is 9 times 56. And so this is just 2 cubed times 3 squared times 7. Because 56 is 8 times 7, 8 is 2 cubed. And from here, GCD is just you take the smallest of each prime factor. So since there's no 2 in the top one, it's just 2 to 0. And then times 3 squared, it's the same for both. And then 7, and then 13 to 0, right? So this just becomes 3 squared times 7, or 63. All right, so this is kind of the easy approach. I think the other one might. The next one, it's just a great time now to go over the Euclidean algorithm. And it might not be more efficient for this column, but I think this is probably a good example since we are working with kind of big numbers. So essentially, what it says is that the GCD of, let's just call these two numbers, m and n, is equal to the GCD of, now let's just say that m is greater than n. Okay. Doesn't matter, but it's equal to this. So essentially the greatest common divisor of two numbers is equal to the greatest common divisor of their difference and one of the numbers, and the smaller of the two numbers. Essentially what this does is it allows you to simplify the problem by making the numbers smaller and easier to work with. And I think you guys can verify or try to do on your own why this is true. But for now, you can take it for granted. So now we have this. And essentially, you can kind of just keep on applying this idea over and over again until you get which numbers you can work with. So we subtract 819 minus 504. This is 315. And we can apply it again. So 504 minus 315. This is 189. And yeah, so 315 minus 189, that is 126. And I think at this point it's pretty clear. Yep, and so on. At this point, I think it's pretty clear that it's 63, but just for completeness, we can keep on going. So GCD is 126 and 63. And one last step. Which is 126 minus 63. And now, voila, now we have the same number. So obviously the GCD of 63 and 63 is just 63. So this is our answer. Yeah, as Ria said, this is a pretty easy method where you don't have to figure out any kind of prime factorizations. You can just do subtraction over and over again. Yeah, it's very powerful. And this is also a pretty, it's a lot more, I think it's a more efficient way to show that two numbers are relatively prime, or the GCD is 1 using this method. But I don't think we have an example of that. So either way, just know, just know this idea. It's very, very useful. All right. Okay. So the next, let's see, 63. So the next slide is divisibility rules. Honestly, I don't want to write this all out. So why don't we, as we go through this, just type in the chat if you know what the divisibility rule is. All right. So start with 2. Yep, it's even numbers. How about 3? All right, the sum of all the digits is divided by 3. This is actually kind of interesting. So if you want to know why this is the case, just know that since everything is in base 10, you can write any number. So let's just say the numbers A, B, C as 100A plus 10B, C. And then when you divide this by 3, you'll see that 99A is divisible by 3. So is 9B. So you can kind of just subtract them off since they're all divisible by 3. So this like becomes A plus B plus C. They have the same residue mod 3. And this always works because all powers of 10 are 1 mod 3. I forget if we covered that. But yeah, that's also why the divisibility rule for 9 is the same as 3. It's because 9 divides 9, 99, 999, etc. Okay, I see Ria has gone on her own tangent here. So yeah, 4 is the last 2 digits is divisible by 4. This is because 100 is divisible by 4. So any number that like has the last 2 digits divisible by 4, divisible by 4 must be divisible by 4 because the rest of the digits are all like multiplied by 100. With 5, it is last digit is 0 or 5. With 6, it's just divisible by 2 and 3. There's no special one. 7, there is, I think, a rule. It's very useless if there is. The only way you can know is to actually like try it out with 7. With 8, it's.
I think there was a rule that the last 2 digits, it's thing or something. I don't really remember, and I don't think it is too easy to remember.
Yeah, so there may or may not be one for 7. I don't know. I have never used it if there is one. So with 7, there's just divide it out. There's, I don't think, easier way. With 8 is the last 3 digits because 1000 is divisible by 8. That's kind of the idea with all powers of 2. 9, some of it is divisible by 9. 10, it means it ends with 0. 11 is, I think, the most complicated one, which is the alternating sum of the digits is divisible by 11. And I honestly don't know how to explain it right now. And the alternating sum, if we take.
Let's do plus minus, plus minus, plus minus, plus minus.
Like 143 is just 1 minus 4 plus 3. And there's an example problem later on. Covers this, so I'm not too keen on doing it right now. All right, other rules. I have no idea what this is supposed to mean. And we're moving on.
I also think that like it's pretty easy to identify for like 2-digit numbers. There's whether it's divisible by 11, but also like there's a rule that like I think it's not too easy to see if it's divisible, but you could just like calculate. So you have 11 times 13. You would just like do the 13 sum of the digits of 13, and that would be like 4, and then you just put it in between like the 1 and the 3, so it would be like.
I mean, at that point, you might have to just multiply it out.
Yeah, but it's useful for like 18. You could use that for 18.
That only really works with the T's, right? I guess. But this
it
is
also
kind of
works with this. You just.
What's 429?
Yeah. So.
Okay. Well, either way, we are kind of pressed for time, and we probably won't finish, but that's okay. So
Yes and yes. The answer is yes and yes.
Yep, the answer is yes and yes. The sum is 45 if you just add up all the digits. I guess a way to make it easier is just you can ignore 3 and 9 when you're like adding them up, since it's definitely if you're checking divisible by 3. But you can kind of ignore ones that are already divisible. It makes it a little bit faster. This one might take a little while. Not really. Oh. Have at it. Right, the answer is no. Yeah. I actually didn't do this math in my head by myself, so yeah, good job anyway. This. For divisible by 12, just check if it's divisible by 3 and divisible by 4 separately. And if it's divisible by both, then the answer is yes. And if not, the answer is no. All right, the answer is yes. You can see 48 is divisible by 4, so it's divisible by 4, the whole thing is. And the sum is divisible
And
by
then you just add up all the stuff for 3.
Yes. Yes, and you'll see that it works. All right, this is the, okay, try it out. This is a separate, not separate, just a different perspective. All right, so with this question, we combine the rules for 2 and 3. So we know that A must be first even, or else it's not divisible by 2. And then the sum, the whole thing must be divisible by 3. So the sum right now is 10 plus A. So we know that A is either 2 or 8. Those are the only ones that make it. So the sum is, so that A is even and the sum is divisible by 3.
There aren't too many values of A. 2, 4, 6, 8.
Oh yeah, A does represent a digit, by the way.
Yeah, and it also has to be divisible by 3. So you just check them 4.
Yes. Okay. Also, you missed 0, but I guess that kind of, oh well. Okay. Next one. Yep. So I see some of you got it. It's very interestingly enough, the exact same answer, 2 and 8. The sum right now is 9 plus 6 plus 7 is 22. And so we need to be a multiple of 3 and a multiple of 4. And the only ones that work are 2 and 8, since only like 20 and 80 are divisible by 4. 50 is not. All right, last problem. Since we're actually running out of time, I'm just going to show the answer right now. Well, anyway, the answer is 3, but sorry, yeah, it is 3. And the idea is that when you see a very symmetric system of equations like this, you can just add them all up, and essentially it just becomes 3 times A plus B plus C plus D. And very conveniently on the other side, you're just left with 5P. So since we know that P is prime and that these are integers, this must mean that P is 3, because P must be divisible by 3, and the only prime number divisible by 3 is 3 itself. All right, and A plus B plus C plus D is just anything that adds up to 5. All right, this was kind of a weird problem, so if we didn't get it, don't worry about it. But I think it's just pretty cool to just use some of the ideas behind like the definition of prime numbers in a setting that's not strictly number theory. All right, so if you have any questions, you can ask them. Otherwise, I'll see you next week. I'll post the slides on Classroom too from all of what.
Thank you. Bye.
All right.
Bye. Bye.
Bye. Take care.